What's up, team? Today we're talking about solving systems of equations by using a process called elimination. This is the third of three ways that we use to solve systems of equations. We did graphing, we did substitution, and this is elimination. So again, you can do any of these, any of the ways, but sometimes it'll be easier to use one way versus another. So here's how we're going to use elimination. So say you're given a system of equations like this. Our first equation is x minus y equals 11. Second equation is 2x plus y equals 19. That's challenging. There's a lot going on there. We can't just graph those. They're not in slope-intercept form. We can't just do straight substitution. They're not like solved like y equals blah, y equals blah. We just put them together like we did for substitution. Not happening. There is another way that we can do this though. But before we dive into this example, I want you to we're going to talk about solving equations for a minute, and I'm going to challenge you to think about solving equations in a slightly different way than maybe what you're used to. So everything I'm about to do is it's concepts you've seen before, but in a slightly different way. And it's going to help us understand how we're going to solve this system over here. So say I have this equation, x minus y equals 11. And say for some reason, I wanted to add 5 to both sides. Could we do that? I think absolutely we could, because the equation says the value of this stuff is the same as the value of this stuff. So if I add 5 to the left and I add 5 to the right, this is still a true statement. I don't know that it doesn't help us advance the problem at all, but it's a true statement because we added the same thing to both sides. Okay, so I'm hopeful that you're in agreement there. Let's look at something else. What if instead of adding 5 to both sides, what if we added, let's say we added x to both sides, plus x. Well, now all of a sudden we have 2x minus y equals x plus 11. Again, I don't know that that actually helped us advance this problem, but my hope is that you see that this is indeed true. Because it is. We were given some statement, we added the same thing to both sides. This statement's still true. It doesn't like get us closer to solving it, but it's a true statement. Okay, let's combine these two ideas a little bit. Let's say that we have this equation, x minus y equals 11, but let's say that we also know that x equals 5. Let's say we know that this is true. Generally, what we would do is substitute this value in for x. I want to challenge you to think about this in a slightly different way. If we know that x and 5 have the same exact value, then wouldn't it be okay if to one side of this equation I added x and to the other side I add 5? Because they mean the same thing. If x has the same value as 5 and 5 has the same value as x, then I should be able to add 1 to one side and 1 to the other side, and I'm not changing the truth value of this statement at all. So that would look like if I added x and I added 5. And I know that feels uncomfortable. The only reason that this is okay is because we have this equation telling us that x and 5 in this problem actually have the same exact value. So that's what makes it okay in this context. Again, this doesn't actually help us reach where we want to go, but this idea of adding two different things that have the same value, that's the crux of what we're about to be talking about today. So make sure you understand this piece before moving forward, because if this doesn't make sense, what I'm about to do is going to make even less sense. Okay, we have this system of equations over here. We know that x minus y equals 11, and we also know that this same x, if we have two of these x's plus the same y, equals 19. Our task is to figure out what x and y combination make both of these equations true. So what I'm going to do is I'm going to utilize this technique that we just used over here. If I know that x equals 5, then I can add x to one side, 5 to the other. Now, the way I'm going to use it over here is a little bit different because we have y's and other stuff going on. But what I know, if I look at this equation, I know that 2x plus y equals 19. And I also know that x minus y equals 11. So what I'm going to do, here, I'll rewrite this. I'm going to rewrite our 2x plus y equals 19. So here's like our problem, and this is me doing some work. This is the second equation. Didn't change it, just copied it. And what I want to do to this is I'm going to add 11 to both sides. But the way that I'm going to add 11 to both sides is a little bit sneaky. So on the right-hand side, I'm just straight going to add 11. And you might be asking, why 11? How did I know that? Well, I got it from right there. I didn't really do any math. I just said, oh, well, this one has an 11, so I'm going to add 11. But this also tells us that 11 has the same value as x minus y. So in addition to adding 11 to the right side, I'm going to add x minus y to the left side. So I'm adding plus x plus a minus y. And this is where things like get really uncomfortable because you're like, what the heck are you doing here? There's 3 different things you're adding, right? It's the same idea. If we know that x and 5 have the same value, then I can add x to one side, 5 to the other, and it doesn't change the truth value of what's going on. That's what's going on here. If I know that 11 has the same value as x minus y, well, then I can add this stuff to one side, and on the other side, I can add 11 because they have the same exact value. Pretty cool. And watch what happens when we do this, too. So if I have 2 x's and I add 1 more x, that's 3 x's. Y plus a negative y. Well, if I have 1 y and you take it away, I have no more y's left. And then I would say equals 19 plus 11, which is 30. Now we have a nice, cool equation. And we learn by dividing both sides by 3 that x equals 10. So that x equals 10, that is the x coordinate of our solution. Pretty cool. So again, this move here, it's a little bit sneaky, and I acknowledge that, but it's true because we know that 11 equals this stuff, so I added 11 here, added that stuff here, I solve for x. Now, just like substitution, what we're going to do is we're going to take that x equals 10, and we're going to plug it back into either of these 2 equations. We get to pick top one or the bottom one. It really doesn't matter which one you go with. I'm going to go with the top one, and the reason being is not because it's any better, but because it looks easier to work with. So I'll take our top equation, x minus y equals 11, and I'm going to sub in x equals 10. So I'm going to say 10 minus y equals 11. I'm going to subtract 10 from both sides. Negative y equals 1. Kind of gross. I don't want to know what negative y equals. I want to know what y equals. So I'm going to divide this by negative 1, divide this by negative 1, and learn that y equals negative 1. So our solution to this system is 10 comma negative 1. So that means you can plug in 10 for this x and for this x. At the same time, you're plugging in negative 1 for this y and for this y, and both of these equations will be true. Okay, stay tuned. I got one more example for you. All right, here's our next example. This one should go a little quicker because I don't have to do all the background work here. We already know what we're doing. So 2 equations, negative 6x plus 5y equals 1. And the second equation, 6x plus 4y equals negative 10. This one's a little bit grosser, but we know that there's some solution where the x value, these 2 x values are the same, these 2 y values are the same, and both equations are true. So similar to the last one, I know that negative 10 has the same value as 6x plus 4y. So I'm going to add negative 10 to the right side of this one, and I'm going to add 6x plus 4y to the left side of this equation. And when I do that, I'm going to take a big shortcut here, and I'm going to use a phrase that I don't love to use, but it's something you might hear, and it looks like what's happening. So essentially what we're doing here, this is the phrase I don't like, is we're adding these equations together. Now, the reason I don't like that is because we're not technically adding equations together, but it looks like it. So here's what I mean by that. I'm going to grab a different marker here. If we simply draw a line underneath and put a big plus sign right here, this looks like a big old addition problem. And we're adding like terms together. But really what's happening is on the right-hand side, we're adding this business. The left-hand side, we're adding this business to the equation. But it looks like one big addition problem. So we can kind of treat it as such, really. So watch what happens here. Negative 6x plus 6x Well, that just goes away. That ends up being 0. Nice. 5y plus 4y is 9y. And then 1 plus a negative 10 is negative 9. Well, 9y equals negative 9. Let's divide both sides by 9. And we learn that y equals negative 1. That was pretty quick. So this is, even though I don't like that phrase, adding the equations together, you see how it expedites the problem. It makes it go pretty quickly. Now we're going to take this y equals negative 1, and we're going to plug it into one of these two equations. These both look pretty simple to me, or like the same amount. Neither looks simpler than the other. They both have a single negative sign. They both have a couple variables. So I'm just going to pick the top one because it's on top. So I'm going to take this y equals negative 1, and I'm going to plug it into that top equation. So negative 6x plus 5y equals 1. But now I'm going to replace the y value with negative 1. So negative 6x plus 5 times negative 1 equals 1. Get our PEMDAS on, and we'll solve this equation for x. Negative 6x, 5 times negative 1 turns into a negative 5 equals 1. I'm going to add a 5 to both sides now. And we learn negative 6x equals 6. Oh, how strange. X also equals negative 1. So our solution to this problem is the point negative 1 comma negative 1. So if we plug negative 1 in for x and negative 1 in for y, our claim is that that is the only possible combination of x and y coordinates that will make both of these equations true. Okay, this is how you solve equations using the elimination method.